Hey everyone, how are you? In this video, we are going to solve the Leetcode problem of the day, and the problem is count submatrices with all ones. The problem category is of medium level, and yes, it is medium, I would say. And let us try to solve it in an easy way. The input given in the problem is a two-dimensional binary matrix. Basically, we can say that we have a 2D array. When we say it is binary matrix, it means the matrix or the 2D array is made up of either 0 or 1. The elements are either 0 or 1. The output we need to give in the problem is submatrix count. We need to count the number of submatrix that have all ones. So try to find out all the submatrix which has all ones. Now, first of all, let me tell you what are valid submatrix. Let us say this is your given input. You are given a two-dimensional binary matrix in which the elements are 1 or 0, right? This is the two-dimensional data. Basically, you can say that you have an array, and inside this array, you have multiple arrays. So this is two-dimensional. It has three number of rows and three number of columns. But the number of rows and the number of columns can be different as well. In this example, it is same. But our approach to solve the problem is not going to depend upon the number of rows and the number of columns being same or different. Now, first of all, let us understand what are valid submatrix. Basically, each element can be a submatrix. For example, for this element, if I just want to choose one element and I want to say that this is a submatrix, I can say that, okay, I want to choose the row number 0 and the column number 0. So I can say, let's create a 2D array or 2D submatrix from our given input in which we have just one data, 1 or 0, but we have just one data, one number of row and one number of column. So it is a valid submatrix. Just choosing one element is valid submatrix. I can also say that this is a valid submatrix. Here I want to choose just one row, 1 comma 0, and I can say that this is a valid submatrix. I have one number of row and two number of columns. Similarly, I can say I want to choose this particular data. It is also a valid submatrix where we have one number of row and three number of columns. I can represent this like a 2D matrix in this way. I can say I have an array in which I have just one row, 1 0 1. So 1 by 3, one number of row and three number of columns. I can say that this is also a valid submatrix where I have two number of rows and one number of columns. I can represent this in a two-dimensional matrix, something like this. I can say I have an array in which I have two number of rows, right? So this is also a valid submatrix where I am choosing two rows and one column. It is 2 by 1, two rows, one column. So this is valid submatrix. This is a valid submatrix. This is a valid submatrix. This is a valid submatrix where I am choosing two rows and two columns. The whole matrix is a valid submatrix where I am choosing three rows and three columns. This is a valid submatrix where I am choosing two rows, row index 1, row index 2, and all the columns. But this is not a valid submatrix. Here I am choosing two rows, but in the first row I am choosing two columns. In the second row I am choosing one column. This is not valid. This is also not valid. Basically, you will have to ensure that if you are choosing three number of rows, in all those three rows, you have to choose all the columns you are choosing. I cannot say that I want to choose one column and in the second column, I don't want to choose the last element. This is not valid submatrix. So basically, you have to form a rectangle. This is a valid rectangle, right? Of size 1 by 1. So this is valid submatrix. This is a valid rectangle of size 1 by 2. This is a valid rectangle of size 1 by 3. This is a valid rectangle of size 3 by 1, right? This is a valid rectangle of size 2 by 2. This is a valid rectangle of size 2 by 3. So basically, we need to find out how many valid submatrix or how many valid rectangles I can create that have all ones. So let's do it for this particular data where we have a 3 by 3, 3 rows, 3 columns, 2D matrix. I can say that each element is a valid submatrix, right? So every element which is a 1 can be counted as an answer, right? Because if I just say this is a submatrix, it has all ones, right? So it can be counted. So similarly, every element which is just a 1 can be counted. So we have 6 number of elements which is just a 1 and we are going to count it. But we have more rectangles which we can form, or we have more submatrix which we can count that have all ones. This is a valid rectangle, right? This is a valid submatrix in which we have all ones. This is also a valid submatrix which is different than this one, but it has all ones as well, right? So we can mark this one as well, right? Now, this is a valid submatrix as well. It has all ones, so this can be counted as well, right? So we got 1, 2, 3, 3 more. So now our count is 9. Now let me rub this off to find out more rectangles or more number of submatrix. This is a valid submatrix. This is a valid submatrix. It has all ones, right? Even this is a valid submatrix, but it doesn't have all ones, right? So I need to count these two as well. So now my count is 11, right? So let me write this. I have a 11 count. This is a valid submatrix. It has all ones. So now my count is 12. And there is one more, which is this one. This is also a valid submatrix where we have all ones. So now our final count is 13. There are no more valid submatrix which are going to have all ones. We have other valid submatrix as well. Like this is a valid submatrix, but it doesn't have all ones. It has 0, right? So we are not going to count this. We are not going to count this as well. It has zeros. So the final answer for this one is going to be 13. Now let us try to solve the problem. And to solve the problem, the first step is to understand how can you find all the submatrix. And I have already told you that you can say that a submatrix is nothing but a rectangle which you can cut out of your data, right? Or out of your 2D matrix. Now, when we talk about a rectangle, let me draw this. This is a rectangle, right? Or this can be a rectangle as well. A rectangle has two important data. It has a width and it has a height, right? Now, when we talk about the width and the height of a rectangle in terms of a 2D matrix, what we are basically saying that this is the width, right? And this is the height. Basically, I need to find out all the rectangles. So our approach will be either we find out the height of our each data or the width of our each data. If we have one data available with us, we can try to find out the second data as well. Basically, we need to find the width, right? And the height. For example, if I am at this particular data, let us say I am just looping through my data and I am right now at this point. This element itself can form a rectangle, that's one. But I don't know what are the other rectangles this element can form, right? For example, if my pointer is at this particular location, I can say that this is a rectangle. I can say that this is a rectangle, and I can say that this is also a rectangle, right? Now with this element we can form other rectangles as well, but let us say we are just looping through our element one by one. Let us say the flow of our loop is first we are accessing this particular element, then this one, then this one, then this, then this. As of now I have not seen other elements, so let us not bother those elements. But for this element I have already seen this one, this particular element, this element, and this element. So I have to find a way to find out what are the different rectangles which this particular element can form along with the other elements which I have already seen. So I can say that this is my element. What is the height of this element and what is the width of this element? See, the thing is, if I talk about the height, I can say that the height is 2. It can form a rectangle of height 2. Its capacity is to form a rectangle of height 2, right? But the problem is, we are also going to see those elements whose values are 1. Now, when I talk about this particular element, it is 0, right? So even though I can create a rectangle something like this, I don't need to count it. So the height of this element, I can say the height is 1. Basically, the height is 2. It can form a rectangle of height 2, but we are not going to form this. But if we talk about the width, this element is a 1. The left element is a 1. So individually, it can form a rectangle as well, the element 1 itself. And with the left element, which we have already seen, it can form a rectangle of width 2. So from here what I can find is, if I just talk about this element, it can form a rectangle of width 2, height 1. That's the maximum capacity of this. If this would have been a 1, then its height would have been 2, the width would have been 2 as well, right? But since we know that this is a 0, the width is going to be 2, the height is going to be 1. Now if I ask you, if you know about the width, if you know about the height, can you tell me what are the different number of rectangles or what are the different number of submatrix we can count that has all ones? We can do this. Let me tell you how. If I am forming a rectangle with this particular element as my last element, because right now I am pointing to this element, this is the last element I have seen as of now. We are going to see the other elements as well, but as of now we are at this particular element. And now this element can form a rectangle where the width is 2, height is 1. So let us say this is width 2, height 1. This is my rectangle. I have a 1 here, I have a 1 here as well. How many rectangles can it form? It can form a total of 2 rectangles. One is the element itself and the other rectangle is with the left element, 1 and 2. It can form total 2 rectangles. So its width is telling me that it can form total 2 rectangles. So from here what idea I get is, I have to count the height and the width at each point and do the calculation, right? What we can do is, we can initially do a count of either the height or the width. That is, for each element calculate what it can be its maximum height or what can be its maximum width. Let's go with the height. Let's calculate the height first. What we can do is, we can say that if this is my data, we have 101, 110, 110. Now let us calculate the height, the maximum potential height of each element. When I am talking about this particular element, it cannot have a height more than 1, right? Because it doesn't have any element above this. So its height will be 1. Its height will be 0 because it is 0. Although definition wise this is a valid submatrix, but we just need to count those matrix or those submatrix which has ones, right? So let's ignore this. We are going to completely ignore all the elements which are 0, right? So this is 0. Let's ignore this. The height of this element can be 1. It doesn't have any element above this. The height is 1. Now about this element, its height can be 2. This is 1, but above this we have 1, right? So its height can be 2. We are talking about the maximum potential here. So its height will be 2. For this element, the height can be 2, but this element is a 0. So we can say that the height is 1. So its height will be 1. This is 0, so we are going to leave it as 0. Basically, to calculate the height, what you can do is, you can say, okay, what's my current element? It is 1. What is the height of my previous element? It is 1. So 1 plus 1 is 2. Then my current element is 1. My previous element is 0. So the height is 1 plus 0, which is 1. My current element is 0. Let me ignore this. Similarly, for this particular element, my current element is 1 and the height of the element above me is 2, right? Its height is 2. So I don't need to loop back completely. What I can do is I can say, okay, I am at this particular element. This element has a height of 2. I can see it here. So this element will have a height of 3 because it is a 1. Above this we have 2. So the total height is 3. Similarly, for this element, it is a 1 and the element above this has a height of 1. So its height will be this 1 plus this particular height 1 is equal to 2. So the height of this one will be 2. This is a 0. So let's ignore this. Now we have changed our elements. This was our original data. Now this is our data. Let's completely have our focus on this particular data. Now we know that the output for this particular input is 13, and let me tell you how we can find it. For each element, we have already calculated its potential height, right? Now we need to find the width as well for each element. We are again going to run the loop to find the width, because to form a valid rectangle or a valid submatrix, we need to find the height and find the width as well, right? Once we have the height, once we have the width, we are going to do our calculation. Now let's process the element one by one again. When we talk about this particular element, it has a height of 1. Now to find the width, as we have done for the height, like we were at this particular element, so we were looking in the upward direction to find the height. So to find the width, what we can do is, whenever we are at a particular element, to find the width, let's just go in the one direction, which is left. So for this element, the height is 1, the width is 1 because it doesn't have any element in the left hand side, right? So now the maximum rectangle this particular element can be is of size 1 by 1, 1 row 1 column. Now since this element is a 1, I can say that we got one particular submatrix which has all ones, right? Now this element is a 0, it has a height of 0. I don't need to process this. Let's completely ignore this. So now at this point we have processed this element, we have processed this particular element, right? Now let us look at the next element. When you look at this particular element, it has a height of 1. What about the width? To find the width, we have to go in the left hand side, right? When we go in the left hand side, we saw a 0. The moment I saw a 0, we don't need to proceed further. The thing is, if this would have been a 1, and right now we are at this particular point, so we can say that if this particular element is 1, going in the left hand side, it is 1. So yes, we can form a rectangle of bigger size with 2. When I am at this particular point, see my cursor or my pointer is here, right? Now I am trying to find the width. So I am moving in the left hand side. There will be another loop which is going to move in the left hand side to find the width. Now if this is 1, we are going to proceed further to see how much potential width this can go. So if this is 1, I will say that okay, right now I am at this particular point. Let me create my width. It is 2. Let me increase my width. It is 3. If this would have been a 0, then we would have said that okay, my width is 2. Because this is 0, let's break it up. The moment I see a 0, I cannot increase my width because I just need those submatrix which are all ones. So the maximum potential of this particular element is a submatrix of size 1 by 1, 1 row 1 column. So it can contribute to a total of one submatrix which has all ones. So I got one more, right? So let me write it as 2. Now let us proceed ahead and let us process the next element, which is 2. Now its height is 2, right? The moment I know that its height is 2, I can say that this can form a rectangle of size 1 by 1 and 1 by 2 as well, right? So its height is telling me that I can form two rectangles. As of now, I can form two rectangles. We are going to increase the width, but just by looking at the height, I can say that it can form at least two rectangles, right? One of size 1 by 1 and another of size 1 by 2. Now it cannot go in the left hand side because we do not have elements in the left hand side. So for this element, the best potential is to create a submatrix of size 1 by 2, right? The width is 1, height is 2. It can form total 2 number of submatrices. So I have already got 2. I got 2 more with this element. So now I have 4, right? Now let us try to process the next element, which is 1. The height of this element is 1, right? So from height wise, I know that it can have a maximum height of 1. What about the width? Alright, if we talk about the width, we are going to go in the left hand side. This is a 2, right? This 2 indicates that the height of this element is 2. The height of this element is 1. Now imagine this. I have a rectangle of 1 by 1, which is this element as of now. The left hand side, I have a rectangle of 2 by 1. Now with this element, what's the rectangle you can form? I can form a rectangle of width 2, but height will be still 1, right? So from here I can say that my height will be the minimum height which I will get for any element throughout processing my width. The height is 1. I want to create a bigger rectangle. I will go in the left hand side to see the width. Alright, I got a width. This particular element although has a height of 2, but still I can create a submatrix of height just 1, although the width now can be 2. So what we can do is we can say, I have gone in the left hand side and I have increased my width. Width is 2, height is 1. How many submatrix can you count now? I can say that one individual element is one submatrix and one 2 by 1 submatrix as well, right? So I can count a total of 1 and 2, 2 more. I got 2 more submatrix, so I can say my count is 6. Now, the next element is 0, let's ignore this. The next element is 3. This 3 is telling me that I can count a total number of 3 submatrix with all ones. One is this one, another is this one, another is this one. Just by looking at the height, I can tell that I got 3 more. I cannot go in the left hand side to increase the width, so let's just count the heights, right? So now I got total 9. I already had 6, I got 3 more, so 9. Now, when we are at this particular element, try to understand what are the different rectangles we have to cover. As of now, the answer is 9. The final answer is 13, right? This is the last element which is going to contribute to more number of submatrix because the next one is 0, so we are going to ignore this, right? We want 4 more. How can you get those 4 more? See, the logic is, if I am at this particular point, what are the different rectangles or what are the different submatrix? It is 1, 2, right? These 2 I can get just by looking at its height. The height is 2, so I can say 1 and 2. I got 2, right? So I got 2 more. Now, when I extend in the left hand side, this is the logic you need to understand. The moment I extend in the left hand side to create more width, our logic will be to maintain the height. The minimum height is going to be maintained, right? Because this has a height of 2, this has a height of 3, right? Still, this is the rectangle we can form, right? This is not valid rectangle, right? So we have to maintain a minimum height. This has a height of 2. We got 1 and 2 more here. Now, when we extend in the left hand side and we found that the height is 3, we can say that the minimum height we are maintaining is 2 coming from the left. We are not going to change its value. I am just talking about this particular loop when we are pointing at this element. When we are going in the left hand side, at this point I have a height of 2. At this point I have a height of 2. But at this point also we are going to count 2 more. And the reason is, just by looking at this element, I got 1 and 2, right? Now I am trying to extend. So now this is the rectangle I am forming. And since the height here is 2, the height is 3, but this has a height of 2. So the minimum height will be taken into account for the current loop. So we can say that at this point, when I am extending to create a bigger submatrix, a bigger rectangle, so this is the one I need to count, but I will not count it just one. I will count a total of 2 because this has a height of 2, this has a height of 3. The minimum height here is 2. So I can count this particular rectangle and this particular rectangle. If this would have a height of 1, if these elements would have been 0, at this point, I will just count when extending in the left as 1. I'm not going to increase the height, right? But since it has a height of 3, I can increase it. But I'm not going to increase it till 3 because this is 0. And that is why we are maintaining the minimum height variable, right? Now let me show you the solution of this approach and then you will understand more about this. First of all, we are counting the number of rows and the number of columns in our given matrix. Then we are looping through our data, but we will not loop through the first row. Because first of all, we are trying to find the height, right? For the first row element, the element itself are the height, right? Because they do not have any element above it, right? They do not have any element above this. So for the rows, we are going to run a loop from the index number 1, that is basically the second row. And we are going to run the loop for each column. And if our current element is a 1, we are going to update its height. We are going to say that its height is equal to the current value plus the height above, right? So once we have calculated the height, we can say that the result is 0. That is, now we are going to start counting the number of submatrix. Now we are going to run a simple loop to access each element, and if our current element has a height more than 0, so now we are going to maintain a minimum height variable. The minimum height is going to be the current height, and now we are going to loop back. From my current element, I am going to loop back in the left hand side. So for k in the range of c to -1, -1, that is basically looping in the left hand side or looping reverse. If our current element is 0, we are going to break, because if it is a 0, we cannot extend any more in the left hand side. But if it is not, then we are going to update our minimum height and then we are going to add this minimum height in our result. That many number of submatrix we are going to get contributed to, and then finally we can return the value of result. That's our complete logic to solve this particular problem, and we can submit this, and this is going to pass all the test cases for this. So yes, you can see that we have passed all the test cases. Memory wise it is good, runtime wise it can be improved, but this is a fair solution because the input size given is not so high. The time complexity of this particular solution is going to be the number of rows multiplied by number of columns multiplied by number of columns. So r multiplied by c square, but the space complexity is going to be constant. So guys, we have solved this particular problem, and that's it for this video. If this video has explained you the problem, the solution approach, the different scenarios of this particular problem, then make sure that you are hitting that like button. But if you have not subscribed to my channel as of now, then make sure that you subscribe to the channel as well. And I will see you guys in the next video. I want to see you guys in the next video. Thank you for watching this one.